Have you ever looked at a map and noticed how South America and Africa fit together like puzzle pieces? That's not just a coincidence. About 200 million years ago, these continents were actually joined together as part of a massive supercontinent called Pangaea. But here's the wild part. The ground beneath your feet is moving right now, slowly carrying entire continents across the planet's surface. Let's dive into the fascinating story of how Earth's continents move. The answer lies deep beneath the surface. Earth isn't just a solid ball of rock, it's more like a layered onion. At the very center, you have a scorching hot core made mostly of iron and nickel. The outer core is liquid, swirling with molten metal that generates Earth's magnetic field. The inner core is solid despite temperatures reaching about 5,400 degrees Celsius, because the pressure there is so immense it forces the iron to remain solid. Surrounding that is the mantle, a thick layer of semi-solid rock that's so hot it can actually flow, kind of like extremely thick honey. This mantle makes up about 84% of Earth's total volume. On top of all that sits the crust, the thin rocky shell we live on, which is only about 5 to 70 kilometers thick, depending on whether you're under the ocean or beneath a continent. The crust and the uppermost part of the mantle together form what scientists call the lithosphere, and here's the key. This lithosphere is broken into massive pieces called tectonic plates. These tectonic plates are absolutely enormous. We're talking about slabs of rock that can be thousands of miles across. There are 7 major plates and dozens of smaller ones, and they're all floating on that semi-fluid mantle below. The North American plate, for example, includes not just the continent of North America, but also part of the Atlantic Ocean floor. The Pacific plate is almost entirely oceanic, covering most of the Pacific Ocean. The Antarctic plate surrounds the entire continent of Antarctica. The African plate contains the African continent plus parts of the Atlantic and Indian Oceans. These plates are constantly moving, but incredibly slowly, typically just a few centimeters per year. That's about as fast as your fingernails grow. Some plates move faster than others though. The Pacific plate moves at about 10 centimeters per year, making it one of the speediest. So what makes them move? The engine driving this whole system is heat from deep inside Earth. The core is incredibly hot, reaching temperatures of about 5,400 degrees Celsius. This heat comes from 2 main sources: leftover heat from when Earth first formed about 4.5 billion years ago, and ongoing radioactive decay of elements like uranium, thorium, and potassium deep in the mantle and core. This heat causes the rock in the mantle to move in giant convection currents, similar to how water circulates in a boiling pot. Hot rock rises toward the surface, cools down, then sinks back toward the core to heat up again. These churning currents act like a conveyor belt, dragging the tectonic plates along with them. Additionally, when oceanic plates sink at subduction zones, their weight helps pull the rest of the plate along in a process called slab pull. And at divergent boundaries, gravity causes the elevated oceanic ridge to slide downward and outward, a force called ridge push. This movement creates 3 main types of plate boundaries, and each one shapes our planet in different ways. First, you have divergent boundaries, where plates move apart. The most dramatic example is the Mid-Atlantic Ridge, a massive underwater mountain range running down the center of the Atlantic Ocean. Here, the North American and Eurasian plates are pulling away from each other. As they separate, hot magma from the mantle rises up to fill the gap, creating new ocean floor. This process is called seafloor spreading, and it's literally making the Atlantic Ocean wider by about 2.5 centimeters every year. Iceland sits right on this ridge, which is why it has so many volcanoes and geothermal features. The island is essentially being torn apart as new crust forms beneath it. Then you have convergent boundaries, where plates crash into each other. What happens next depends on what type of crust is colliding. When an oceanic plate meets a continental plate, the denser oceanic plate gets forced underneath in a process called subduction. This creates deep ocean trenches and chains of volcanoes on land. The Andes Mountains in South America formed this way as the Nazca Plate slides beneath the South American plate. The Mariana Trench, the deepest place on Earth at about 11 kilometers deep, formed where the Pacific Plate dives beneath the Philippine Plate. When two continental plates collide, neither wants to sink because continental crust is less dense than oceanic crust, so instead, they crumple upward, forming massive mountain ranges. The Himalayas are still growing today because the Indian Plate keeps pushing into the Eurasian Plate, raising Mount Everest a few millimeters higher each year. This collision started about 50 million years ago when India, which had broken off from Gondwana, finally crashed into Asia after drifting northward across an ancient ocean. The third type is transform boundaries, where plates slide past each other horizontally. The San Andreas Fault in California is probably the most famous example. Here, the Pacific Plate and the North American Plate are grinding past each other, causing frequent earthquakes. Los Angeles sits on the Pacific Plate while San Francisco is on the North American Plate, which means Los Angeles is slowly creeping toward San Francisco at about 5 centimeters per year. In about 15 million years, they might become neighboring cities. The friction between the plates is enormous, building up stress until it's suddenly released in an earthquake. This theory explaining how continents move is called plate tectonics, and it's actually relatively new. For centuries, people noticed that continents seemed to fit together, but they had no explanation. In 1912, a German scientist named Alfred Wegener proposed the idea of continental drift. He pointed out that identical fossils of ancient plants and animals were found on continents that are now separated by vast oceans. For example, fossils of Mesosaurus, a freshwater reptile, were found only in Brazil and South Africa. A fern called Glossopteris was found across South America, Africa, India, Antarctica, and Australia, suggesting these landmasses were once connected. He also noticed matching rock formations and similar geological features on different continents. Mountain ranges lined up perfectly when continents were fitted together, but Wegener couldn't explain what force could possibly move entire continents, so most scientists rejected his ideas. Many ridiculed him, suggesting continents couldn't plow through ocean floor like ships through ice. It wasn't until the 1960s that scientists finally pieced together enough evidence to support plate tectonics. Advances in ocean floor mapping revealed the mid-Atlantic ridge and patterns of magnetic reversals in rocks that proved seafloor spreading was real. As magma cools at mid-ocean ridges, iron minerals align with Earth's magnetic field, which periodically flips. This creates symmetric stripes of normal and reversed magnetization on either side of ridges, like a geological tape recorder. Studies of earthquakes showed that they clustered along plate boundaries. Scientists could now track the exact locations and depths of earthquakes, revealing the shapes of subducting plates. Suddenly, everything clicked into place. Plate tectonics explained not just continental drift, but also why earthquakes and volcanoes occur where they do, how mountains form, and why certain areas are more geologically active than others. The theory was revolutionary, fundamentally changing how we understand our planet. The implications are staggering. Plate tectonics means Earth's surface has been constantly rearranging itself throughout our planet's history. Continents have collided, broken apart, and drifted across the globe in a slow dance lasting billions of years. About 335 million years ago, most of Earth's landmasses merged into Pangaea. Then, around 200 million years ago, Pangaea began breaking apart. First, it split into two supercontinents, Laurasia in the north and Gondwana in the south. These continued fragmenting into the continents we recognize today. And the movement continues. Right now, Africa is slowly splitting apart along the East African Rift. In about 50 million years, the eastern part might break off completely, creating a new ocean. Australia is drifting north toward Asia at about 7 centimeters per year. In roughly 50 million years, it could collide with Southeast Asia, creating new mountain ranges. The Atlantic Ocean keeps widening while the Pacific Ocean shrinks. Some scientists predict that in about 250 million years, the continents might merge again into a new supercontinent, sometimes called Pangaea Ultima. Plate tectonics doesn't just reshape the land, it profoundly affects life on Earth. When continents split apart or collide, they create barriers or bridges for species, driving evolution in new directions. Mountain building changes weather patterns and creates diverse climates. Volcanic activity releases gases that affect the atmosphere. Some scientists even think plate tectonics might be essential for life, because it recycles carbon and other elements between Earth's surface and interior, helping maintain stable temperatures over billions of years. So the next time you feel an earthquake or see a volcano erupt, remember, you're witnessing the awesome power of plate tectonics in action. The ground beneath your feet isn't solid and unchanging. It's dynamic, constantly moving and reshaping our planet. In the grand scheme of geological time, Earth's surface is as fluid as the ocean, with continents riding across the globe on massive tectonic plates. It's a reminder that our planet is alive in ways we rarely consider, constantly transforming itself on timescales far beyond human experience. That's how Earth's continents move, slowly, relentlessly, and magnificently.